Welcome to Lecture 21 of Topology on topological manifolds, normal spaces, and separation axioms. We are again in mad survey mode, so you'll forgive me for not proving much in here. My aim is really just to say enough for the statements of the major theorems of Chapter 7 and Manetti to be understandable. And, well, anyway, let's give it, as they say, the good old college try. Although I'm starting more and more, the longer I teach, to not be certain that that saying really makes sense. Not talking about you guys, but anyway. If you're watching this video, you're probably not one of the people I'm being disrespectful towards, yes. Anyway, a subbasis of a topological space is a family, P, let's say, of open sets such that finite intersections of that family form a basis of the topology. Remember, basis means that if we take unions of those sets, we can get everything, right? Anyway, so here, here's an example. The Euclidean topology, if we just take the raised to minus infinity and the raised to plus infinity, right? If you take those kinds of sets, you can get the open intervals because you can intersect this ray and that ray and get AB for A less than B. And of course, the set of all open intervals gives a basis for the Euclidean topology. So there's an example of a subbasis in case you want one. All right. So we have some pretty high-powered theorems in here to state, not to prove. Let me zoom in a bit so we can read them more comfortably. There we go. So theorem by Alexander. Let P be a subbasis for X if every cover of X made by elements of P has a finite subcover, then X is compact. So that's pretty neat because, you know, it frees us of the more pesky problem of considering an arbitrary open cover, right? So if you got a subbasis, it suffices to look at covers formed from the subbasis, you know. So that's a little bit freeing. It's, you know, a little bit nicer to work with as a criteria there. There's also Tikhonov's theorem that the product of an arbitrary family of compact spaces is compact. Now, to do this theorem justice, we have to talk about the topology of an arbitrary product, and I don't think we've done that. And I don't think it's easy either. So I'm skipping over quite a bit there. And I feel like there's additional details in Moncrief's on that point, like the box versus the product topology. Like I said down here, the topology of infinite products is a bit tricky. I'm not getting into it, but I believe Chapter 7 Manetti has a slightly different approach to Moncrief's. I speculate. When I took a course from Moncrief's many years ago, I remember stuff about the box versus the product topology, and I remember being very scared of it on the test. But anyway, I don't know. It's that fussy part of. Anyway, I'll shut up. Anyway, so the product of any number of connected spaces is connected. So these are, you know, really comforting theorems, right? Wow, you know, so you take the product of compact stuff, you still get a compact thing. You take the product of connected spaces, you get a connected space. And here, to make it interesting, we're not talking about finite products. We're talking about possibly infinite Cartesian products, yeah? All right, so there's that. Next up in Chapter 7, we flip over to looking at something called paracompactness. And you might say, what is that? So let's talk about it, all right? What's up with that? Yes. So a family of subsets in a space X is locally finite if every point X in X admits a neighborhood V in the neighborhoods of X, right, such that the intersection of V with the family is non-empty at most finitely many sets in the family. So this is locally finite. So you can find a neighborhood of the point such that neighborhood meets only finitely many members in your family of subsets. That's locally finite. So for any locally finite family of subsets, you have the union. The closure of the union is the union of the closures, and so that implies that the union of a locally finite family of closed sets is closed. Okay. There's a lot more to say here. I'm just giving you some of the high points, right? But you can also take two covers, like a cover U and a cover V, and you can say that the U cover refines the V cover, or is a refinement of V, if for every I there is a J such that UI is a subset of VJ. So the refinement is something that it's like smaller, smaller sets. I suppose in the world of YouTube videos, maybe you could think of a refinement sort of like turning up the resolution on the video or something, you know. I don't know, but in such a case, you have a function that actually accomplishes this, right, from I to j, with ui a subset of v of fi for all I. If you have that, then that's called the refinement function. And he actually does give some explicit examples of that if you read Minetti here. I mean, he mentions if you take two covers and you intersect them, then that gives you a refinement of both of the covers. And he actually gives the refinement function in the book if you look at it there. Oh man, I was going to tell you where. I was going to tell you where, if I can find it. One moment. Where'd that thing go? Come back to me. Where'd you go? Yeah, example 7.13. There he's got the actual, refinement function for this intersection. Right there. Anyway. A topological, listen to me. Whatever. Come on. So uncivilized. What's wrong with me? A topological space is called paracompact if every open cover possesses a locally finite open refinement. So if you can take any open cover you have and you can find a cover which is like a little bit more, a little finer, then and that more fine cover is locally finite, then that means your space is paracompact. So paracompact. So it's certainly compact implies paracompact, right? Because compact means that every open cover has a finite subcover, and finite implies locally finite, because you can't if you have a finite subcover, you can't meet the cover in infinitely many places, right? Because there's only finitely many things, only finitely many elements to the cover, right? So yeah, so definitely compact implies paracompact, but the converse, of course, is not true. There are spaces which are paracompact but not compact. That is true. Let's see here. Sorry, this lecture is kind of short on examples. This lecture could be vastly improved with about 30 examples of all these terms, yeah? So, sorry about that. Let's see here. But hey, you want to improve this lecture, go to the comments and say, hey, an example of a blah is a blah. There you go. You'll improve it just like that with the comments. But let's see here. Let X be a Hausdorff space. If X is exhausted by compact sets, then X is paracompact and locally compact. If X is connected in paracompact and locally compact, then X has an exhaustion by compact sets. So at first I thought that these were just converses of another, but they're not. Notice the lopsidedness of the statements. Like this one, we're just having exhaustion by compact sets, and then the conclusion is it's paracompact and locally compact. In this number 2, we're also assuming connected paracompact and locally compact. Then you get an exhaustion by compact sets. So yeah. All right, so every locally compact second countable Hausdorff space is paracompact. All right. And there's a harder theorem. So section 7.3 of Minetti has proof of these things, although it doesn't have proof of Stone's theorem, and it has a reference to it. And Stone's theorem simply says this: every metrizable space is paracompact. So if you can put a metric on your space, it's going to be paracompact. So, so paracompact spaces are in abundance, yeah. So next up, we will talk about section 7.4, which talks about topological manifolds. I have a whole book on topological manifolds by, I think, John Lee. And so there's a lot that you can read about this. And so this is just really sort of a 10,000 foot view of things. There's a lot more to say here. But this is a good start, I suppose. So a space M is called an n-dimensional topological manifold if M is Hausdorff. If every point in M has an open neighborhood homeomorphic to an open set of Rn. And if every connected component of M is second countable. Now, the main push in this section 7.4 is to replace number 3 with paracompactness. That's eventually corollary 7.29 in this section says that you can replace number 3 with paracompactness. And so that's why we're talking about paracompactness before. That said, I have seen manifolds defined not as a topological space. It is possible to define a manifold as an abstract set with an atlas of bijections, and then you can, if you want to, build a topology on the manifold through the chart structure, and in so doing, you'll end up with a space which is Hausdorff and I think paracompact if you fussed on it. But so like fine. Yes, we can start with a manifold which already has a topology, but there are other ways of thinking about a manifold besides this. I'm just saying. I mean, I've seen it in courses. I'm not sure. I haven't seen polls like what is the dominant viewpoint in all mathematical researchers. I have no earthly idea. I do know that there are things called sheaves, and I know that everything we're doing in some sense is probably going to be replaced by that viewpoint, but it's a lot more abstract. So anyway, more about that later. So let's see here. Open subset of Rn is n-dimensional manifold. All right, yep, because it's Hausdorff. It is literally homeomorphic to an open set. I mean, it is the open set. So, and the same is true for open subset of Cn. Let's see here, what else? The sphere is a topological manifold of dimension n, and the open set you can see is you just take the sphere, you delete the pick your point, pick the antipodal point, delete it. Then you've got a punctured sphere, which we've proved is homeomorphic to Rn via the stereographic projection. That's actually page 13 of this book. Wow. Also, the real projective n space is a n-dimensional manifold, and each point, in fact, lies in the complement of some hyperplane H, like this. Now, yeah, okay, so, So here, he writes things like this. I mean, it's doing something like identifying the equivalence classes with a point or something. Anyway, to be more explicit, example 5.21 on page 96 gives the homeomorphism that's this. From this equivalence class, you can map it to this point in Rn. But in order to do that, you need to know that x naught is, not equal to 0, which either puts you in what? X naught's positive or x naught's negative, which is to say a half space, right? Which is, a half space is the complement of a hyperplane. So that I would say if you want to, I wouldn't waste too much sleep over understanding what the sentence means. Each point lies in the complement of some hyperplane H. Just look back at example 5.21, page 96. That, I think, is really what's meant by that sentence. Projective n-space is a complex projective n-space is a 2 n-dimensional topological manifold by much the same. And I would just add that if you have a finite dimensional vector space over the reals, that's a linear manifold, right? Um, oof. Is a topological vector space a manifold? How did we define topological vector space? What was it? Do you remember? Not sure I remember. Was that this lecture or the last? Well, I feel like that might have been the last lecture. I think this is from lecture 20. At the very end of lecture 20, I had, what was a topological vector space is a vector space V with a Hausdorff topology where a vector addition and scalar multiplication are continuous. So if it's Hausdorff, I'm not sure if a topological vector space is necessarily a topological manifold. I'm not sure about that, because Menotti does mention that these three conditions up here that define topological manifold, they're not they're minimal. Like, you can't take away any one of them and still have it. And there are spaces which have, one of these but not the other two, and vice versa. So like, it's not, you really need all three, which makes me a little worried that the topological vector space, yeah, okay, it's got Hausdorff, and oh, well, it's definitely not n-dimensional, because you don't have homeomorphism to Rn necessarily. So yeah, topological vector space would not be an n-dimensional manifold. But you might ask the question then, well, what's an infinite dimensional manifold, right? And so there you've got to find some kind of reference space to use as your token infinite dimensional object, right? To put the manifold in correspondence with. So I guess that's for another day, isn't it? So anyway. But anyway, for a finite dimensional vector space, it's definitely a linear manifold, definitely a topological manifold. And I would say that, vector spaces are really the quintessential manifolds. When I think of a manifold, I do start by thinking about vector spaces. I mean, that's not everything, okay, but it does give you a lot of it. Because, of course, manifolds are curved, right? Vector spaces have this global coordinate chart, and everything is a little bit too simple, but anyway. A topological manifold is locally compact in Hausdorff. Each connected component is exhausted by compact sets. That's pretty nice. Every topological manifold is paracompact. That's what we were saying. And if M is paracompact Hausdorff such that any open neighborhood is homeomorphic to an open set of Rn, then M is the topological manifold, which is just to say that you can take the definition we gave and replace number 3 with paracompactness. All right, so the rest of this lecture, we're talking about the issue of separability, and so first thing on that list is, well, we've already talked about Hausdorff before. That's the first sort of idea of separating points with open sets, right? But you can also talk about a space being normal if it's Hausdorff, and you can take disjoint closed sets. So like A and B are two closed sets. They're not meeting, right? They're not intersecting. And if you can find open set U and open set V such that those don't intersect either, and they contain respectively A and B, if you can do that for arbitrary pairs of disjoint closed sets, then the space is said to be normal. All right. And normal spaces are interesting. Every metrizable space is normal. And every paracompact Hausdorff space is normal. So, yeah, there's that. So, if anybody says that they're normal, you can say, oh, I guess you, are you metrizable? And then they'll look at you and say, shut up, nerd. Or something like that. I don't know. This is just horrible technical meaning for the word normal. And then that brings us to section 7.6, which is the separation axioms. This terminology is introduced by Tizzi, I'm probably mispronouncing that, in 1921 as the, I'm definitely mispronouncing this, Trenbarked sign axiom. So wrong. So wrong, whatever I just said. So sorry. Hopefully I haven't inadvertently insulted your mother or something. I don't know, but let's see here. So a space is called T0 if distinct points have distinct closures. All right. T1 if every point is closed. In other words, the singletons are closed sets. T2 if points that are distinct are contained in disjoint open sets. T2 is also known as Hausdorff. All right, we can separate points. T3, you can take a closed set and a point not in the set, and you can separate them with disjoint open sets. That's T3. T4, every two closed disjoint sets are contained in disjoint open sets. All right, so now you might think that T4 is normal, but remember that normal assumed both T4 and T2, right? So, what more? You want more words? Great, more words. A space is called regular if it is T1 and T3, and it's called normal if it's no, it's not T1 and T4, you dummy. It's T2 and T4. Goodness gracious, who wrote these notes? T2. All right. Good special effects for its time. Let's see here. And so he has the following remark: metrizable implies normal, implies regular, implies Hausdorff, implies T1, implies T0. So these are not, unlike the three parts to the definition of topological manifold, the different axioms here are not independent. They, there is some interconnection. However, you can also illustrate each one of these things with a particular example. So anyway, every second countable regular space is normal. Let me zoom in here. So every second countable regular space is normal. In particular, subspaces of finite products of second countable normal spaces are normal. So you got lots of normal spaces. Great. And also, we have this theorem by Urizen. Every second countable normal space is metrizable. Now that's pretty nice, right? I mean, the existence of a metric is really, well, I find it to be comforting. But so anyway, yeah. And then if you're, maybe take another course in topology, I'm sure you'll study Urizen's lemma and things like that. If you have a deeper point set course than this one, let's say. Anyway, yeah, that's just a quick overview of the separation axioms. In the classical discussion of topology, you might have spent a couple weeks on this, really diving into this and like separating these ideas and seeing examples which illustrate each but not the other. And there used to be a lot more time and energy spent in the topology course on doing this. Certainly when I had topology, it was still about a week of the course, I think. But anyway, there's that. So what's up next? I believe the next thing is homotopy, if I remember right. So yeah, so we're going to do that next, and hopefully I'll have that up soon. Thanks, guys.